What's up? It's Andy, and we're going to talk about exact ODs today, except I'm really tired because it's late at night. Um, yeah, we're just going to take a moment to reflect. So, here's you, and you have two options. You've either taken Calc 3 or you've not taken Calc 3. And then you're either in ODEs or you're. Why is that there? Oh, it's an image. Okay, yep, okay. We're gonna pretend that didn't happen.
Don't you forget about me.
Okay, so you're right there. You either took Calc 3 or you haven't taken Calc 3. And then from there you have two choices. You're either in ODEs or you're not in ODEs. So if you took Calc 3 but you're not in ODEs, there's no oof, you're fine. If you're in ODE right now and you took Calc 3, medium oof. Not you could probably survive. If you haven't taken Calc 3 and you're not in ODE's class. I mean, first off, I would question why you're watching this video, but yeah, medium move. And if you're in ODEs and you haven't taken Calc 3, you're kind of screwed because this is exact equations right here. And this requires you to remember what a partial derivative is and how to integrate partially. What is, yeah, my definition here says the same meaning as in Calc 3. All right, so exact equations. So basically what this means is, like, if you look at two components of an equation, one with respect to x, one with respect to y, and you take the partial derivative with respect to the opposite, then you should get the same thing. That's what exact means. So that's how you tell if you can integrate to find the function that gave you that. And so the function, that would give you these partial derivatives is called the potential function. And that's basically the goal with exact equations. Find the potential function. So the general form here is, you got some function I of x and y. Then you got some function j of x and y multiplied by y prime equal to 0. That's the general form. And if you don't have that, then try to get into that form to see if it could be an exact equation. Now we're gonna, because y prime is dy over dx, we're just gonna convert it over there, and then we're gonna multiply by dx. And then from there, we're gonna check the exactness by taking partial derivatives. Once we're at this step, I kind of messed that up. All right, and now we're either gonna do, we're either going to integrate I with respect to x or j with respect to y, and then we're going to take the partial derivative of what we get with respect to the other, so like, if we did it with I, then we would take its partial derivative with respect to y, and that will tell you what you can eliminate from either I or j. And then you integrate again, and then you should be left with the potential function. So I've got a little example of this process right here. I've got, this function right here, and so yeah, that's a function of x and y. If we take the partial derivative with respect to x, we get I, and we get 3y squared plus 12xy. If we take it with respect to y, we get j, and that's going to be equal to 6xy plus 6x squared plus 14y. Now let's say that we take I, and we already know it's exact, just, take that as a given here. Which you should probably never do, especially because I'm teaching these videos. But yeah, okay, you integrate with respect to x. You get 3xy squared plus 6xy, which is most of that equation right there, except there's a 7y squared right there. And what you do is you can partially derive this. You plug it in there, and you get 6yx plus 6x squared, which you can see, like, in j, it's mirrored right there. So, like, you don't want to account for that twice. So what you do is you subtract that portion right here when you integrate j with respect to y. And that will leave you with just 14y. Integrate that, you get 7y squared. And now you just take what you got up here and what you got there, add it together, you get f. Well, actually, there should be a c here, because integration, but yeah, they're basically the same right there. So, 1 second, I'm gonna get water. Okay, so this is the first example I've got right here. So 2xy minus 9x plus 2y squared plus x squared plus 1 dy dx equals 0. Well, actually, let's confuse you. Y prime. But, you know, that was really for nothing because we're just going to change it back to dy over dx. That's totally a y. Okay, so we've done that. Okay, so let's just multiply everything by dx. So 2xy minus 9x dx plus 2y plus x squared plus 1. That's a bad 2. dy equals 0. And now we're going to check for exactness. So what we're going to do is we're going to do this. Take the partial derivative with respect to y, so 2xy minus 9x. And that's going to give us, let's see, 2x. Do that up here with respect to x this time. And that term doesn't matter, has no x's. That doesn't matter, so all we get is 2x. So it's exact. So that's great. Okay, so now we're going to take one of these and integrate. So I think when I was initially doing the problem, I did that one. And because I'm a bad person, okay, I'm a good person. I'm just, you know, bad at math. We're going to integrate this one. Well, actually not math, just planning. I'm just bad at planning. We're going to integrate this one. So what we do is 2y plus x squared plus 1 dy. We're going to integrate that. We get y squared plus x squared y plus y. And that's great. And then, you know, there's going to be some term out here, which is x, but we're not going to worry about that right now. We're just going to do the partial derivative with respect to x. And that should give us, let me write it down first, I guess. That should just give us x squared, I believe. Is that right? No. Okay. Yeah, 2xy. Yeah, because that doesn't have an x in it, that doesn't have an x in it. They don't matter. That one does. You derive x, and then you just leave the y constant. Okay. So 2xy. And now we're going to, you know, we're going to bring in our I function, the one with respect to x. Notice that one's there, you can't count them twice, so we integrate negative 9x dx, and we get negative 9x squared over 2. Okay, and so now our solution here should be, God, what is it? Okay, y squared plus x squared y plus y minus 9x squared over 2. Plus, you know, some constant because we're integrating. And actually, well, I mean, the diffie-q solution, you set the constant equal to the equation. So that's what we get, and let me just, God, I can't draw a square. Okay, let's just make sure that's what I got. I simplified it, but yeah, that's what you get. Okay. Oh, okay, we're just going to run through this one then. Okay, so we got 2xy equals negative x squared plus 3y squared times y prime. And so what we're going to do is, you know, we want a 0 over here, so what we do is we just subtract that one over, and we're going to, you know, because I skipped steps, we're going to change that into dy dx and multiply everything by dx. And we do the exactness check here. We get 2x when we do the partial derivative with respect to y on this one. And we get 2x when we do the partial derivative with respect to x on that one. So it's exact. And now we're going to integrate, and what we get is x squared y. Yeah, I took that one that time. And now if we derive that, we get x squared, you know, when we're taking the derivative with respect to y. And yeah, okay, so we take the other one, x squared plus 3y squared. We can get rid of that x squared, so that's what I did right there. And so we just get 3y squared dy. Integrate that, we get y cubed. So that means that our solution to this equation should be x squared plus y cubed equals some constant. And if we look at the answer that I got and somehow forgot to erase my work, let's see. Oh crap, what am I missing? Oh, yeah, y x squared. My bad, I miscopied. But yeah, it's, you know, exact ODEs, they're pretty easy. I mean, it's just looking for a potential function, and if you've done Calc 3, you remember how to do that, and, you know, hopefully this was a little refresher on how to do that. If you need extra help, just look at Calc 3 material, and you should be good to go. That's all I got for you today, so...